Let's continue. The next speaker is Alexandr Garbali, who will talk about on non-commutative subalgebras of the quantum toroidal GL MN.
Thank you so much. I'm very grateful to the organizers for inviting me to this event. It's a great pleasure to be here. And I'm happy to talk about this recent work that I was involved with Andrei Neguts. So this is a talk about the quantum toroidal algebra, and I will focus on a commutative subalgebra of this toroidal algebra. And this commutative subalgebra is very much related to questions of integrability, because it's helpful in understanding charges in appropriate integrable models, commuting charges. It's also helpful for building off-shell beta states. So this is largely a motivation for studying this commutative subalgebra. So I guess I should start with some background on the quantum toroidal algebras. And the example that I should use is the quantum toroidal GL1, so the non-supersymmetric one. So many people worked on this algebra, and they kind of felt the algebraic structure for a very long time before this algebra was introduced. And people in algebraic geometry, in symmetric functions, integrable models, they kind of converged to the same thing. And this algebra was discovered independently by several groups. So in integrable models community, people studied deformations of Korteweg-de Vries equation, and Bazhanov, Lukyanov, Samolochikov, they published papers on that. And then later, Lukyanov generalized this to the so-called intermediate long wave equation. And around this time, it became clear to the people working in this area that you need to consider two Heisenberg algebras, and you need to somehow put them together. So Heisenberg algebra, it appeared earlier. So we have elements with negative indices and positive indices. And the commutation relations are, so I'm going to write them here. So this is Heisenberg algebra. And if you look at all the positive modes of the Heisenberg algebra, they are all commutative, and they are basically the same as symmetric functions. And the same can be said about the negative modes. So what you do, you take another copy of Heisenberg algebra, you give it a different name, but it's isomorphic to the first one. And satisfies the same commutation relations. So you take two copies of such Heisenberg algebras, and you deform this relation slightly. So you introduce central element, and a couple of parameters. And the second copy satisfies the same relations with all the generators replaced by these perpendicular versions. So you take two copies of such Heisenberg algebras, and you put them on Z2. So let's say this Heisenberg algebra, I really want to think of it as universal enveloping. So I'm going to call it, instead of Heisenberg algebra, I will call it UQ GL1 hat. So I'm putting one Heisenberg algebra on the horizontal line and the other Heisenberg algebra on the vertical line. So here we have negative modes. Here we have positive modes. And same goes for the vertical line. So we have two subalgebras. And now we need to impose relations between these two different Heisenberg algebras. And this is complicated to do. I'm not going to do this. But it's possible. And what you end up after doing this is that if you look at this Z2 lattice, if you take any line that passes through integer points, it also produces a Heisenberg algebra. So you have SL2Z automorphism of this algebra, and every single line that passes through the origin is isomorphic to Heisenberg algebra. And this is called the quantum toroidal GL1. So I'm going to leave this picture here. I will use it later. Okay, so having this picture in mind, we have a quantum toroidal algebra GL1, and it decomposes in standard quantum affine Lie algebras way into positive, Cartan, and negative parts. So in this picture, we think of Borel subalgebras of quantum toroidal GL1, and we have a left part of generators and the right part of generators, and we can build using Drinfeld quantum double the full algebra using that. So the left part is composed of everything that is to the right of the vertical line, and the right part composed of everything to the right. So I call them U plus and U minus. And the Cartan part is sitting on the diagonal here. So the Cartan part is composed of these generators and these generators, and they're mutually commuting. So the positive parts of the Heisenberg algebra and negative parts, they're mutually commuting. And same goes for the orthogonal decomposition. We can take upper part, lower part, and we have two Cartans which are commutative. Okay, so these are generators of the Heisenberg algebra that I already stated here. And so the parameters here, you can see Q1, Q2, Q3, and you can also see UQT. So they're all related. So Q1 is, it actually doesn't matter how you relate them. So Q1 can be Q inverse, Q2 can be T, and then Q3 is 1 over Q1, Q2. So I will use both Q and T and Q1, Q2, Q3 in this presentation because it makes some formulas simpler. So let me focus on the positive part or negative part, let's say positive part of this decomposition. So a typical situation is that we have two currents in the Drinfeld presentation. We have currents F, and then we swap them at the cost of these rational ratios of two such rational functions. So this is quantum toroidal GL1. Now I'm going to swap. I would like to take this algebra and rephrase it in different terms. And to do that, I reinterpret the relations on the positive half in this way. So you can see that the two parts in this equation, they express symmetry. So if you take expression F times F divided by zeta, you swap Z and W, you will get the same thing back. This is what this equation says, that this expression is symmetric in Z and W. And let's consider Fourier space. We simply take a constant term in this expansion of F, So this is a simple identity. And we call this a map Fn to Z. Z1 to the power n is a polynomial in n. So that's simple. We can take now products of F, Fn, Fm, and substitute this formula. So now we get this polynomial. And this expression here is just symmetrizing the integrand here. So in this expression, I use the commutation relations of F's to put this in the symmetric form. So this is symmetric in Z1, Z2. And this is also symmetric in Z1, Z2. So this is a map from the positive part of the algebra to some rational functions. So this is a rational function. Zeta was written before. It's just a ratio of, I'll put it here. So zeta of x was 1 minus x, 1 minus q1, q2, 1 minus q1 x. So we have a map. I call this a map to Fourier space from generators of the positive Borel subalgebra to rational functions. So this can be called a product. So I'm saying that this is a product, and this is the definition of the product. And this Fourier trick can be performed on arbitrary product of generators, and this gives rise to an algebra of symmetric functions. So this is an arbitrary product, and I call this a shuffle product. And from the same symmetrization that I did before, I can get this identity. So this gives rise to the definition of a shuffle product, and this will be the main algebraic tool that I will use in this talk. All right, so we get, in this way, we get an algebra of symmetric functions, rational symmetric functions with this shuffle product. And it turns out that this algebra is generated by such powers Z and the shuffle product itself. And I will call this algebra S plus. So it's actually not a trivial statement to say that the quantum toroidal GL1 can be factorized in this way. There are several works that were devoted to this statement, but this kind of statements will be, I will use the statements. So we have this shuffle algebra, and then we have the positive part. The negative part is a copy of itself, and then in the middle we have quantum affine GL1, which is the same as Heisenberg algebra. So now I think of the left part as S plus, right part as S minus, or the other way around, and this is Heisenberg algebra. And there are advantages to switching to this Fourier space, because now instead of having these generators F, which are abstract generators, we can actually work with symmetric functions, and we can try to understand their structure. So, for example, if we find two elements in this shuffle algebra, which shuffle commute, because they are symmetric functions, we can probably prove them that they commute on the shuffle algebra side. That means that we also found commuting elements in the positive part of the quantum toroidal GL1. So this is the advantage. And it turns out that it's actually possible to do. We can find many elements, and people back in the late 90s, Fagin and Desky, they found this kind of elements, but before the quantum toroidal algebras were invented. And later on, when people, Fagin and company and also others, when they encountered quantum toroidal algebras, the first thing that they tried was this factorized elements, and often it works. So less trivial situation is taking such determinants. So these determinants, they also provide commutative elements with respect to the shuffle product. And we can define more complicated elements like these ones. So this is given recursively. We take some shuffle products, and we also get elements in the commutative subalgebra, and also these ones. I don't want to spend too much time on this because this is quantum toroidal GL1. I want to talk about quantum toroidal GLNM. Okay, quantum toroidal GLNM. So I'll discuss quantum toroidal GLN, but I really mean GLNM. So GL1 has this nice symmetry, the SL2Z symmetry. In GLN case, this is not true. So we need to change one of the lines. So let's say we change this one. So this is going to be, this Cartan subalgebra will be quantum affine GLN. And this one will be quantum affine GL1 raised to the nth power. So in the quantum toroidal GLN case, the situation, it looks like this. We have two Borel subalgebras. So let's say we have left part and right part. They can be expressed in terms of similar shuffle algebras. So as before, we use the same trick to switch from the Drinfeld presentation of one of the halves to symmetric rational functions, and we get shuffle algebras, which are symmetric rational functions in sets of variables. But the orthogonal decomposition, when we want to take the bottom and the top, doesn't work. So we have a shuffle algebra for the left part and the right part. This is the formula that is given here. But we do not have bottom and right. We need to think a little bit. And this was done in work by Andrei Neguts, which allows you to decompose the algebra in the bottom in this orthogonal way. So I should say probably that these two decompositions, they give rise to different coproducts, which affects the integrable models that we can define. So there is a Drinfeld coproduct and Drinfeld-Jimbo coproduct. If you decompose in this way, you get Drinfeld coproduct. If you decompose in this way, you get Drinfeld-Jimbo coproduct. And for integrable models, it's the Drinfeld-Jimbo coproduct is maybe a little bit better. So I want to focus on this second decomposition. So how do we get the second decomposition? We do not have the symmetry in the quantum toroidal GL1 case. We need to do something else. And this is based on some other interpretation of, on related interpretation of quantum toroidal GLN. You need to consider matrix-valued W algebra. And it's defined with some quadratic relations. I don't want to focus on this formula. I just want to say that the orthogonal decomposition is based on W algebras, which are matrix-valued. So these are quadratic expressions in generators of W algebras, and they are we have some R matrices of GLN, which we need to define these relations. So I don't want to focus on the algebra, on this algebra itself. I want to focus on the shuffle algebra part. So we can, through some complicated process, we can Fourier transform this these elements of the W algebras and get the shuffle algebra part. And as a result, we get the algebra of rational functions with matrix-valued coefficients. So these are the elements. These elements from the previous commutation relations, they have to satisfy some exchange relations with the R matrix, and they also have to satisfy some pole conditions, and there are also Will conditions that are too technical. So the message here is that we are using the same trick with the Fourier space to take the W algebras to a shuffle algebra part. And then we get the double shuffle algebra expression for the quantum GLN. So the shuffle product looks very technical. This is impossible to read. So instead of reading this, I will suggest to do some graphics. So we can represent our matrices using crosses, and this is what I'm going to do next. So this shuffle product is expressed in terms of our matrices R sigma, which are themselves braid lifts of R matrices. So here I'm using the R matrix of quantum affine GLNM. So the graphical representation of the R matrix is as usual. We just draw a cross and interpret it as a matrix living in the tensor product of two representations of UT-GLNM. And in terms of vertex weights, it has weights that can be read from these vertices. So this supersymmetric part here is expressed in terms of epsilon i's. They can be +1 or -1, depending on the gradation of the vector. And this R matrix satisfies all the nice properties in Baxter equation, unitarity, crossing unitarity. So now, using this R matrix, I'm going to write down the shuffle product. So it looks like this. So once again, this is derived from the W algebra expressions. And this is the product that we need to work with. And turns out that in this algebra, we can obtain a very good understanding of the commutative subalgebra. So you take two elements, F and G, and then you put them together using some additional R matrices, and then we symmetrize them with this R sigmas. Okay, maybe this is not very encouraging, so maybe I'm going to give another motivation for this shuffle product. So we have, in this shuffle product, we have basic commuting elements, which we take projectors, raise them to power k, and it turns out that they shuffle commute. And this follows from basic relations of quantum toroidal algebra. But there are other elements which are less trivial, and they are also turn out to be commuting with respect to that shuffle product. So these are the elements. And we can show that they commute and that we can write them in this expression, using this expression. So what is this? So HKI is a matrix which is partially domain wall. And the product of these two H's is a trace which has the labels I and J only on the traced part. So there are some additional projectors in this part. So to prove this relation, we can use some identities involving R matrices. How much time do I have? 20. Okay. Okay, so I will prove this identity, and so I have to show that this expression on the right is a shuffle product that was the beast from the previous slide. So let me start. So we have this shuffle product, and we need to show that it's equal to this partial trace. So I can write the sum as the sum over symmetric group, which symmetrizes strings of labels I and J of different lengths. Because this is a trace, I can insert any matrix on the two sides of the trace, and I'm going to choose a special matrix to insert, which is called the F matrix. So this F matrix is known as the Drinfeld twist, and it factorizes the R matrix. So we have our check sigma, which is equal to F inverse n. So there exists such expression for the R matrix in terms of the Drinfeld twist. And I'm going to use this identity over there. I'm going to use this F matrix. Yeah, so I inserted this F matrix over there for free. And now this summations over sigma can be rewritten in terms of the permutation matrix. So I choose to order the vectors here in a certain way. So j is greater than I, and on the other side, I is greater than j. And the cost of this ordering is permutation matrix. So now I have a combination P times F inverse and F times P. So this combination can be re-expressed in terms of R matrices. So I have P sigma times F. I can re-express it in terms of F and R. So here I replaced F and P with R and F. So the F matrices appear on the outside. And these vectors I and j, this arrangement of indices I and j, is chosen such that the matrices F act very simply on them. So these matrices F there can be chosen to be upper or lower triangular. And because of that, they act diagonally on these particular vectors. So I can act with these Fs on these vectors. And I get back the eigenvalues of the F matrix. So you need to believe me that these are the eigenvalues of the F matrix. So now F matrices are gone, and I have the R matrices here left. I can push them through using the Baxter equation. So they appear on the other side. And on this side, there is some freezing happening. So the indices I and j, they have to propagate in such a way that this upper part freezes. So if so it freezes in this way, and we can read off the matrix elements that appear here, and it produces some additional rational function. So this theta is the same as this theta. And we have two parts here which look a lot like the definitions of the H's, and the R matrices are at the bottom. So then we can just re-express this R matrix as a product of two things, and this is what we get. And if you look carefully at this, and if you remember the definition of the shuffle product, which was basically the same thing but rotated. So I started with a trace of elements of the main wall type, and then I proved that they are equal to the shuffle product. So this is the definition of the shuffle product. So you can do exactly the same calculation, assuming that the F matrix is upper triangular. And if you do that, you will have I's and J's swapped, and this will prove the commutativity of those elements. Okay. So in this way, we obtain some commuting elements of the shuffle algebra. But this is not all. We can actually generate many more commuting elements if we take this kind of objects. So these are partition functions on an n by n grid with R matrices on the crossings. So this is again a partial trace, and this is a matrix in the spaces. Algebraically, this is written as a partial trace of a product of R matrices of GL and M type. And here I have a choice to put a twist. This U is a twist in the boundary conditions, which keeps track of all the degrees of freedom that are being traced. So this Z is a generator in the variables U of with respect to projectors EI. So let's build a generating function of such objects. We take all of these generating functions in the use and put them in a bigger generating function. And turns out this can be expressed in terms of exponential with respect to the shuffle product that appeared there earlier. And the expression is this. So this is a theorem. We get this conic generator partition function as a shuffle exponential, which is expressed in terms of special elements S. And it depends on a bunch of parameters which keep track of the twist parameters U. So these elements S, they can be calculated. So we show, first of all, that they commute, and then they can be calculated in a recursive manner using this shuffle product. And we also have interpretation for these elements in terms of conic partition functions using these R matrices. Okay, so what is this based on? Why does it work? Once again, this works because there exists some algebraic reason for this to work. And that algebraic reason is given by the homomorphism property, or rather isomorphism property, of this expression. So we take a trace of products of R matrices times some element X, which lives in the tensor product of basic representations. And this looks very much like traces of products of R matrices that appeared before, but it's actually not that. You can combine expressions, traces of R matrices that appeared before with this one in a very unexpected way. So if you take this trace and you insert it for the X in the previous expressions, then it will make sense. I mean, ask me if this sounds too convoluted. Yeah, thank you for this. Sorry, I have to go through this again. This is the structure. So that product of our matrices is precisely this. And here, when you go around the cone, around the tip of the cone, you pick up a parameter U, which keeps track of the vector label that goes around the tip. So that parameter U, it counts the winding of loops. If you think about this in terms of lattice paths. So there are lattice paths that connect the external edges, and those give you the matrix elements. And then there are lattice paths that wind around the tip of the cone, and those give you the parameters U. So this is the structure of the, sorry. So these are the R matrices that, that build the cone for you. And these traces, they make the cone itself, and X's are the twists. But actually here X's can be not just twists, they could be any elements of the shuffle algebra. So if you put here any element of the shuffle algebra, this expression here gives back an element of the shuffle algebra. So this is an anti-isomorphism. So if you put two elements, if you take instead of X, if you take A times B, this trace will give you back B times A in an isomorphic shuffle algebra. But for commutativity purposes, it doesn't matter. It's anti-isomorphism or isomorphism. So, for example, the elements H that I just showed before, they're these expressions, they're these traces of projectors. And this generator Z can be also expressed in terms of Z. in terms of psi, this expression. Okay, summary. So we have a commuting elements EI of the shuffle algebra, and they are commuting for purposes, for simple purposes, because because this comes from a connection between shuffle algebra and the toroidal algebra, and we can get more complicated elements by applying this non-trivial isomorphism to the simple elements. So we get such elements here. And in addition to this, we can compose this isomorphism psi with various projectors and embeddings. And we can get maps from shuffle algebras of different quantum toroidal algebras. So we have maps of such compositions, and we can get, if we find commuting elements in one algebra, we can use this map psi to get commuting elements in a different algebra. So here we can take a very small algebra, and here we can take a large algebra, and we can map the commuting elements from one to another. And those elements S and also analogs of those elements K can be obtained using this general linear map psi. So all of this gives trace formulas for various commuting elements of the shuffle algebra. And if you want to get back to the quantum toroidal, you need to take the inverse Fourier transform. So this is the end of my talk. Thank you so much.
Yeah, thank you. Have questions?
Yes, thanks, Sasha, for the nice talk. Just curious, what is this Z for GL1? This Z commuting element?
Where was that?
The cone. Nothing.
It's not working.
Yeah, but that's not going to solve his problem.
I can't navigate. Should I use this for? Z of GL1.
This cone you had, it defines some commuting element too. You with this nice exponential shuffle formula.
Yes.
If you look at it for only for GL1, you can define similar objects.
Okay.
What are they?
Yeah, good question. Thank you. Thank you. So this kind of element for GL1, right?
H you show already, no? It was
It's the same thing.
Yes. Z is the.
Okay, fine.
It's the interesting.
This is the one. So what makes this object GLN or GLNM is that the external indices are free. So this is the matrix in endomorphism from these spaces, the vector products of these spaces, to vector products of these spaces. This is a GLN object. If you want to go to GL1, it will be a scalar, and you take vacuum expectation. So you need to put here boundary conditions to be zeros, or like you just select the upper corner of the matrix. So all these zeros and all these zeros, this gives you GL1. So if you take this object with such boundary conditions, all the zeros on the external edges, you get a generator of commuting elements in quantum toroidal GL1.
But are they already known, or is this?
Well, they were studied in a paper by Ajit Guna and myself. This was written in that paper.
I see. But they were new. They were not known from the Fagin Jimbo Miwa.
They contain the Fagin Jimbo elements, and they contain other elements as well. So the Fagin Jimbo elements in this picture. So we're talking about elements which live on this line. And this H's, they are like power sums. Fagin Jimbo elements, they behave like elementary symmetric functions. If you look at these ones, they behave like power sum symmetric functions. Oh, sorry, homogeneous symmetric functions. But you can also get the power sums themselves in precisely this way. It's a bit of a, it's not complicated. It's manipulating these formulas. So this exponential that I showed you, this exponential, you can imagine this thing as being in a GL1 shuffle algebra. So this will be a GL1 shuffle element, and you have a bunch of parameters u. You can play with those parameters, and if you choose those parameters in different ways, you can generate different elements, including Fagin Jimbo, including the dual ones, including the s's themselves. You can get this exponents s also from this exponential by taking some clever limit. And as a result, you get explicit formulas in terms of R matrices. This conic kind of expressions for all of them.
Nice. Okay, thanks.
Sasha, I have a general question. So there's a famous result by Schiffman and Becerra that there's a surjective homomorphism from UQT of GL1 hat from the quantum toroidal to double affine Hicke algebra. So what happens in the super case, GLN/N? Like in particular, like, can you recover some super McDonald operators? Or?
Yeah. I don't know, but this is something to work on because in this picture, if you this is a to do in the to do list. So when you recover those super McDonald operators, those will be the starting points for studying the integrable model on the proper integrable model of quantum toroidal GLN. Just like McDonald operators are zero twist versions of the transfer matrices on quantum toroidal GL1.
Right, but they haven't been computed. Like you don't know, you did not compute them yet, right? So you don't know.
I didn't talk about representations at all here. So if you want to talk about representations, then
no, it's just at the level of the algebra, right? So it's the algebra homomorphism. So you have quantum toroidal surjects into Daha for GLN, spherical subalgebra, and on that plot that you have, the vertical axis are the McDonald operators in the power symmetric basis. So now I'm asking, does similar construction exist for super case?
No, I don't think so. So first of all, super case is very unstudied. There are two works on super case, and they're not rigorous. I mean, there are some. I mean, they're partially rigorous, but the super case is not studied. You shouldn't expect anything in the super case at the moment. I don't think it's difficult. It's just technical.
It hasn't been done yet. Okay.
Yeah, it can be done. Yeah. I think super case is the same as the GLN case.
Can you say a bit more about the possible integrable systems applications of this? I mean, are you hoping to get integrals of motion for integral?
Right. Yeah. So I need to go back to quantum toroidal GL1 for that. And in the quantum toroidal GL1, so there is a nice representation that is called Fock representation. The vector space is infinite dimensional. It's graded with the vectors labeled by Young diagrams, and the degree is given by the number of boxes in Young diagrams. And on that representation, you can write beta ansatz, and this is what many people did. In particular, Feigen-G, Bamiva did it algebraically, and they found that the transfer matrix is an elliptic deformation of the integrals of those functions that I showed before. So if you look at so if you take these functions, you take this function, you integrate it together with vertex operators, Shiraishi Jing vertex operators, that gives you a McDonald operator. And if you turn this into an elliptic version of this function and integrate it with elliptic versions of Shiraishi operators, then you get the transfer matrix of that integrable model, quantum toroidal GL1. And that elliptic integral, it degenerates to intermediate long wave equation of Lukyanov, and further generates to quantum cortical freeze equation of Pozhanov, Lukyanov, Zamolodchikov. So in that sense, it gives a deformation of those integrable models. So you make this elliptic, and you get an integral commuting Hamiltonian. You can also make this. I mean, you can try to make this elliptic, and you can get another Hamiltonian, and same applies to these operators. So they give you a whole zoo of commuting operators which live in this transfer matrix, the space of the generated by the transfer matrix coefficients. And this is all GL1 case. And in GLNM case, it's not studied, but the structure is expected to be the same. So all those products of R matrices that I showed, they will give rise to similar operators that will commute. If you make them elliptic, they will commute. They will correspond to the charges on that integral model. So this is a motivation for potential. Sorry?
Why do you need to make them elliptic for that?
Well, they become elliptic when you take the trace. So the trace is infinite dimensional, and you start with something non-elliptic, and when you take the trace, it gives you something elliptic. It's a technical computation.
Thank you.
I have a short question. You construct some commutative algebras, so do you have some control or conjectural control about their size?
Yeah.
And do you think are they maximal in some sense?
I think they're maximal. I don't know how to explain that, but the size is clear. It's so if you take this part, this is algebra of symmetric functions. You take n of those, and that gives a complete description of the size of the commuting algebra. Isomorphic to this one. Exactly. And there is a way to identify precisely. So here you can call some polynomials elementary symmetric, homogeneous symmetric power sums. And there is a precise way to identify the elements that I showed, traces of R matrices, with some twist, with the particular elementary and homogeneous and power sum polynomials. So it's completely, this algebra is as clear as that algebra over there. It's just that the product is complicated, but.
Okay, let's send the speaker. Now we have short 5 minutes break, 6 minutes.